cannot detect two point sources when they are close than the high lobe of the iris. With these fluorescence molecules, when they are excited by a laser beam, only a smart number of these molecules are able to interact and emit energy. So as you see here, just a small number each time of laser emission can be detected. So by repeating, by illuminating by different times with a laser beam, a small portion of protein, we are able to locate the single molecules, and then by taking all the single acquisition to obtain an image which is sub-diffracted, which means that it overcomes the intrinsic diffraction limit when you can see in the first frame, which is a classical result of an optical system. So it is a post-processing, because the frame is what the optical system is able to acquire, but with this post-processing procedure, with this sparse restoration, and by summing all and stacking all the different acquisitions, we are able to obtain a protein which is close to the ground truth, which is lower than about 10 nanometers. Okay, the system is very simple. We have the unknown y, the delta y, sorry, which is the blurred and noisy undersampled image. And undersampled image because it is in an optical system is in with the limit of diffraction of the other disk. The unknown is x at final read, the solution to restore, whose dimensions are much greater than the undersampled image. The noise in this system is a Poisson noise, and basically we have a model parameter, which is a linear parameter in this very basic model, which is the product of a convolution operator and downsampling operator. At the bottom you can see the solution X and the data, the noise image on the right. Difference between Gaussian and Poisson noise, you can see just in the first column at the bottom, you see that the three small molecules are completely, it's completely impossible to discriminate, because the convolution seems like a Gaussian or one source. And the noise on the top, we see the Gaussian, which is more or less equally distributed everywhere, independently of the intensity of the source. In the Poisson case, in some sense, the noise is relative in some sense, where in the background we have low absolute noise, and while the intensity in the middle, the noise is high. The best variational model for this sparse restoration for Poisson noise is this one. We have to minimize the function, which is the sum of a delta fidelity term, which is a Kullback-like divergence. We just here write only the terms which depend on a x, which means because this we want to find the point x star, not immediately. And the classical regression terms in the first case, in the best case, is the L0. No. The idea is just to consider an approximation of Kullback-like divergence by means of its second-order Taylor expansion. Again, we neglect all the terms of the expansion which do not depend on x, and we obtain this approximation of the L0 with Kullback-like divergence which is a sort of relative square, because we have yj at the denominator. If we consider a matrix, diagonal matrix W, we can just write the relative square as the norm of ax minus y with respect to the weighted norm. So we can consider this basic weighted L2 L0 norm problem, where now the data fidelity is the weighted norm, and again the penalty timing is zero norm. The zero norm leads to a NPR problem, and so the idea is to approximate, relax in some sense, these L0 norms with one, we see now, with a different norm which approximates with continuity the L0 norm. We have some examples. To do that, we consider the complex envelope of the functional in one dimension, on the L0 functional in one dimension. The L0 functional is the blue curve with the dot point here in the zero, which is approximated in some sense by its complex envelope, which is the red function in one dimension. This is a generalization by the Gaussian case, which is the expanding paper by Soubise, Blanc, Ferrol, Science, Imagine Science of 2015. And we obtain this same penalty timing terms of the paper by Science with normalized by the square root of the data 1. Again, even if the sum is convex envelope, the penalty is still non-convex. And the important fact in the Poisson case is that now the penalty depends on the data. In the Gaussian case, the penalty phi g is the red. It can be plotted by the green curve, which is the same independent of the intensity of the data y. In the Poisson case, you see that the penalty term change its shape, its behavior, when the data has more intensity, 0.5, it approximates better than the other case, the zero norms. Otherwise, it is much more relaxed. So, by using this 1D simple computation, we extend to n squared case of the matrix n times n, and we consider again a similar functional g w c e l 0, which is the sum of again the w norm and the sum of the singular relaxed convex envelope of the L0 norms. In general, just for the case of particular case of matrix A orthogonal, the new functional in class dimension is the convex envelope of the case of L0, not in the general case. But anyway, we have the same result of the original paper. The global minimizers of the original function, which means the L0 function, are still global minimizers of this new relaxed function. And the new relaxed functional remains sum of the local minimum of the original. So it can be used. It is continuous. And see, we can just compare here the case the Gaussian case G of 0 and weighted. We have different penalty. Here, the red norms means that the penalty now depends on the data Y, different from the Gaussian case in which the norm of the column will not necessarily are always the two norms. The computation of these norms, column norms for large metrics, is not simple. In the Gaussian case, it is just a supermatrix of a sort of BCC matrix. It's a bit different. It's a GBCCG matrix, a series blank, without some matrix, without some row and column. But in the case with the W, each column has a different norms because each column has different weights. Here you see, in the case of Gaussian case, we have only 4 different colors for L, because 4 L is the factor, the ratio between the final and the grid and coarse grid. You see on the right that here we have n square different values. But by means of the FFT is able to compute as well in few computation all of these n square taking the values which are necessary for.
Claudio, sorry, you have just 1 minute left.
The problem has to be solved by strategy which is able to work with these penalty terms. The idea is to consider a sequence of L1 convex optimization problems which locally approximate and majorate the original one. We have a closed form computation for this differential. So by means of a weighted L1 minimization, we can compute by a forward-backward strategy the solution of the relaxed model. The idea is just to us to use a fast iterative software solving algorithm with this weighted terms on an X.
Sorry, Claudio, your time is kind of up. So if
simulation, we evaluate. Sorry. Okay. Okay. So.
Can you hear us?
Yes.
Okay.
Oh, okay, perfect.
Okay, if you can wrap it up.
Yes.
Thank you.
Okay, just reevaluate the result. We consider the chapter index, which is the ratio between the correct molecules and the sum of the correct ones and the false positive and false negative one with respect to the radius. So we give a tolerance in terms of pixels. So if you are close to this tolerance, the molecules can easily considered as correctly detected. And we consider here the result of our WCEL0 model. The chapter index are higher than the other case, the basic Gaussian case and the deep storm algorithm. And to have an idea of the result, the last slide, we consider on the bottom one single acquisition with the optimal system, and the result with this post-processing schedule. The Gaussian model CEL0 the Poisson proposed model and the deep store, and the localization is a bit better with W0. This is the last zoom. You can see here in the middle that the two different structure of the proteins can be resolved better than the other two models. Thank you, and sorry for all the technical problems.
Thank you, Claudio. No problem. So we actually don't have a lot of time of questions. Just if someone has a very telegraphic one. Okay. If not, let's thank
you
Claudio again. Sorry for the missing question and the technical problems. So we can move to our next speaker, which is Ronnie Ramlau, and that will. Hello. Okay, we can see you. Perfect. So Ronnie will present a talk in collaboration with Bernard Stadler, Roberto Biasi, Mauro Manetti, entitled Parallel Implementation of an Iterative Solver for Atmospheric Tomography. So please, Ronnie, the floor is yours. Ronnie, I guess that if you put your presentation full screen, we will. Yes, we can see it. Perfect.
We cannot hear you.
Yeah. Ronnie, we cannot hear you. Yeah, you, Ron, it seems like you have the microphone on.
So,
yes, now we can hear you. Yes.
Now you can hear me?
Yes, yes, we can.
Okay. And now you see everything?
Now we see your screen. Yes, we don't see.
And you hear me?
Yeah, we see your screen, not the presentation, but your screen.
Oh, you see, you don't see the presentation?
No, it seems like it's frozen though, because I don't see you moving or anything.
So something moves now?
Nope.
Okay, let me just state the system is totally crap. I actually don't know what to do. That's good. That is.
Okay, now if you want, you can send us the PDF of your presentation and we can just share our screen if it works better, and you just can ask us to change the slide.
I'll try that. So just send it to you.
Yes.
Should be there in a sec.
Laptop, quickly, even quicker.
So that should work, right?
Yeah, now we see your presentation.
I mean, that is, and you hear me, and that's somehow nice. Okay, then I just do it now. Is that okay for you?
Yes. Yes.
Okay, let's try it. Okay, sorry for all these problems, but I have used many of these systems, never before Jitsi, and I hope I will never use it again. This is about just a short report on parallel implementation of an iterative solver for atmospheric tomography, and as Alessandro already said, it's joint work with Bernadette, Roberto, and Mauro. And what is it about? It is about, oh, I have to somehow, yeah. So introduction, it's related to the construction of the extremely large telescope, the ELT. You see that actually over here in this area. So that's the ELT, just so that you get an idea how big it is. It's really going to be the largest telescope on the planet with a primary mirror. That's the one in here of 39 meters. And the problem that we are dealing with, that due to atmospheric turbulences, the images that you are recording are blurred. So that's the thing we have to deal with. And in order to conquer that problem, we use adaptive optics. And adaptive optics is basically kind of a mechanical computational device to correct for these turbulences. You see the turbulences, that's the red and blue parts. It's basically patches of hot and cold air that are mixed and that are moved by wind over the telescope. And how do you deal with that? You have on the sky, on the night sky, you have guide stars, bright stars, and some really bright natural stars or just laser stars. And you have down here at the telescope, you have wavefront sensors. That's a sketch here of the wavefront sensors. And these wavefront sensors detect the light from these laser guide stars, from the guide stars. And they measure the distortion of the wavefront. So that's the incoming wavefront. It's a plane here from the star. Then it goes through the turbulence here. And after that, it's kind of crashed, crumpled. And this wavefront sensor down here detects this shape of this wavefront. And based on these measurements, we compute kind of a correction, which is later on then applied to this deformable mirror. So we have some actuator commands that are used to deform the mirror. And then this mirror basically has the negative shape of this distortion here. And then basically at the end, the reflected image on this mirror is then sharp again. So that's the idea. We are in particular concerned with the tomography problem. And a tomography problem you would like to correct for a large field of view that we can actually see here. The assumption is that you have different turbulence layers in the atmosphere. Usually we think of a number of turbulence layers might be between 3 and maybe 20 that you have in the atmosphere. And you would like to reconstruct the turbulence in these layers. So now somebody is coming cleaning. Hang on a second. Please, no, not yet. Thank you. That's always when you give a talk, somebody wants to clean your office. Anyway, so in order to solve that problem, to reconstruct the turbulence from this light coming from the guide stars, you have to solve this inverse problem. It's basically a limited angle tomography problem. And what we are using for the reconstruction is regularization in a Bayesian framework. We compute a maximum a posteriori estimate, which is given by this formula here. More or less, it's Tikhonov with a covariance matrix of basically representing the statistics of the atmosphere, and here's some noise covariance matrix for the measurements. And the challenges are in particular that the operations are quite many, and we have to reconstruct in a very short time. So we have to do a very sophisticated implementation. And well, the solvers that we actually look at for atmospheric tomography are the first one that ESO, the European Southern Observatory, actually prefers. It's kind of a matrix vector multiplication. So what you do is you have your forward operator, that's the A that I presented before. That's a huge matrix. You pre-compute regularized inverse in soft real time. So you do that not in hard real time. And then you have the inverse and you apply this inverse to your data. So it's basically your reconstruction step is a matrix vector multiplication. what is nice about that, you can really parallelize that easily, and it's also pipelinable. Pipelinable means you can actually start the computation once the first patch of data tickles in. But of course, it's a lot of operations that you have to do. What we prefer is an iterative approach. So what you do is you do a discretization to obtain some kind of sparse operator. Then you solve the system with, for instance, PCG, and you can actually use only a few number of iterations, and you get that by doing some preconditioning, some proper preconditioning. This is very fast because you have a sparse discretization, and we also can use updates of the parameters that can be done on the fly. Whereas in the matrix vector multiplication approach, you have to do that. You have to invert the matrix several times during one observation because the position of the stars are actually changing. Okay, so, and we looked at how this can be done on a computer. And maybe first the finite wavelet approach for the wavelet approach for the atmospheric tomography problem. So we used for the discretization wavelets. See here some of these wavelets. Why did we use that? Well, first, of course, wavelets have good approximative properties. You need only few coefficients for a nice representation of the wavefronts or the turbulences, and also the discrete wavelet transform is quite fast, so you have O of n operations in principle. We used WC3 for the computation, and what did we do? So everything here is now in a wavelet domain, so that's basically Tironov, the Tironov equation that you have to solve in the wavelet domain. So this is the tomography, the atmospheric tomography operator in a wavelet basis, which is unfortunately as a matrix not sparse, but these covariance matrix, the statistics, that's a diagonal operator in a wavelet basis, which is nice. And you could solve that by using PCG. We actually also have a Jacobi preconditioner, but still, as this matrix A is not sparse, it's not really fast. So what we do is we use A in a bilinear basis. In a bilinear basis, it turns out it is sparse. But of course, then we have here a bilinear basis, and here we have a wavelet basis. So we have to switch in between, and we are doing that by applying the wavelet transform and the inverse of the wavelet transform. And as this is O of n, it's really fast. Okay, so yeah, let's go to numerical simulations. The numerical simulations were done on the real system. I mean, we really use the specs of the real system that will run on the telescope. That's the so-called MAORI, the multi-conjugate adaptive optics relay. So that's a picture here of the dome of the telescope, the ELT, and here that's where MAORI is located. You see here the size of this small guy here, so it's really a huge thing. We have the test configurations. That's actually the real test the configuration that MAORI has. So we have 9 wavefront sensors that collect the light of 9 guide stars. The first 6 wavefront sensors have quite some high number of sub-apertures. It's 80 squares, so it's 80 by 80 patches of light that actually measured, and 7 and 8 and 9 relatively small wavefront sensors, only with 4 by 4 and just 1 by 1 sub-apertures. As I said, we have laser guide stars, 6 lasers are shot up in the atmosphere and create artificial guide stars. We use also 3 natural guide stars, and layers we reconstruct up to 9, so 3 to 9 layers, and we have 3 deformable mirrors for the correction. So that's the setting. And just the theoretical performance analysis of the method, the matrix vector multiplication compared to FUHA. So this is just here the hard real time. That's the one that you have to apply for each iteration. And we see that the teraflops for each reconstruction using the MVM are much, much higher than the flops that you would actually need for our iterative approach. So it's 1-0 for FUHA here. And for the soft real time, for the inversion of the forward operator, that has to be done maybe every 5 to 6 minutes during the night. There's actually, well, it's probably 10-0 for FUHA, because we don't need any soft real computation time for fewer, whereas for MVM we need quite a lot. Memory usage for MVM, you have to apply the matrix, you basically have to store it somewhere. So you need altogether 53 gigabytes in memory to store that and to apply that. And for fewer, well, we can do that on a phone. So it's clearly the iterative approaches are much, much better than the MVMs. We just have to convince people at the telescope from that. So we need much less flops. That's what you see here compared to MVM for hard real time. And yeah, also we have here we have a matrix-free implementation, which really saves a lot of memory. Okay, now the parallel implementation on RTC hardware. I mean, it's nice to have an algorithm, but it's much, much better to really when we really have it on the hardware implemented. And Bernadette did that in order to compare. So she did it on a multi-core CPU in C++ using for parallelization OpenMP. And she implemented that on our supercomputer Radon 1. And she did actually computation on one node of Radon 1. And this node had actually 2 8-core Intel processors there. And to compare with, everybody says doing the computations on a GPU is always much better whenever you have problems in speed. So we did everything also on a Tesla V100 GPU. And for the implementation, also Bernadette used QDOT 10.1. And here you actually see the runtime independence of the number of PCG iterations. And what you see here is first, well, it's not true. But that always the GPU is doing the best computations or the fastest computation, because here we see for 3 systems, that one would be a multi-conjugate adaptive optics, a multi-object adaptive optics here, and L-tau is a laser tomography. You see these graphs here, and they clearly say, well, whenever you use the CPU, you're much faster than when you use the GPU. This is was kind of counterintuitive, but we actually had a feeling that might come out. But this is the proof. Here in this case, CPU is better than GPU. Also, the number of layers. The number of layers is not such a big problem here. So it increases the computation time just a bit. Also, the number of threads, the optimal number of threads that we are using for the computation here is going to be 6. So with that, we are reaching almost the goal of having the computation done in 2 milliseconds. Almost, not quite. What is the bottleneck here is still the memory latency and not the computational throughput. So the communication between the processors and the communication needed to read the data and store the data is much heavier than the computation itself. Okay.
Sorry, Ronnie, you have 1 minute at most.
That's enough. What I actually want to say here is, with this picture, it's still true that GPU solves problems if you have these problems. So if the system, the red lines here are always the times for the computation times for the GPU, that's the green one for the CPU. And if the system is big enough, then at some point GPU beats CPU. You see, just the other way around, but always GPU beats CPU. And the point for the telescope is we are still in the area, we are around here somewhere, where the CPU is better than GPU. So for the next telescope that we are building after the ELT, GPU might be okay. And the last slide that I have here, this slide shows, again, it's kind of a roofline model, which actually gives an idea if the speed of your reconstruction is basically limited by the bandwidth, by the memory, or by the computation. And basically, if it's left of this line here, it's the memory, and if it's right, it's the computation. And you see in both graphs, it's on the left side. So the memory latency is the point that actually slows everything down. And that's actually already everything that I wanted to tell. Thanks a lot. And sorry again for the problems.
Don't worry. It's always tough doing this with this stuff. So Thank you, Ronnie, for the very nice presentation. Does anyone has any very quick question?
Well, you can contact me if you have quick questions, even with long ones.
Yeah, send as many emails to Ronnie as you want.
You might not get an answer, but that's
Yeah.
on a different sheet.
No one guarantees that. All right. So let's thank Ronnie again. So now we have the talk by Lothar Reichel, which will present a contribution made in collaboration with Majed Al-Otaibi and, well, myself, entitled Restoration of Blurred Images Corrupted by Impulse Noise via Median Filter and LPLQ Minimization. So,
yeah, well, thank you.
So I see Lothar has the same problems that I have.
And I see many screens here. It's an interesting.
Yeah, because we are still seeing your screen, Ronnie.
You're still seeing my screen. That's interesting.
Yes.
Well, no.
Okay, perfect.
But now we have to see my screen.
Yes, next step is Lothar's screen.
Lothar, just let's have many of your screens.
If you want, I have.
Yeah, you have the file. But I click on share screen and it doesn't do anything.
Okay, let me.
In fact, I had problems logging in eventually, but that was solved.
Okay, don't worry. I can actually share your slide as I have them. And you can tell me just when you want to switch. It might not be optimal, but it works.
Well, let me see, open. Yeah. Well, I see something here. Is that your screen?
Yes.
All right. Okay. All right. So I guess we are in business then, I suppose.
Yes, I will be your mouse.
All right. So let me just get started then, and I guess I will have to tell you, Alessandro, when to
Yes.
Right? Sorry about that. So anyway, so this is some joint work, primarily with Majed Al-Otaibi, who is a grad student in Kent, and Alessandro, who doesn't need an introduction. But this is based on some older work with people in Bologna. And ultimately, what we are trying to do is we like to do LPLQ minimization, and we want to show you some new tricks we can do. So the starting point is that the vector B delta represents the image which is contaminated by blur and noise. And the noise could be salt and pepper noise, it could be Gaussian noise, and it could be more general impulse noise. A is a matrix which represents the blur, and it's typically singular. And we would like, so what is available is a blur noise contaminated image represented by B delta. And what we would like is the original true image, X true. And we want to compute that from knowing the matrix, the blurring matrix A, and the contaminated vector B delta. Next, please. And so here's an example. So this is an image which has been contaminated by motion blur and 70% salt and pepper noise. That means 70% of the pixels have been set to black or white. And if we go on, this is what we can do, right? And what is new about this method is that it's fully automatic. And I'll tell you about the details. Next, please. So we are not the first ones here who remove salt and pepper noise and impulse noise. Raymond Chen and his collaborators did that quite a few years ago, but their methods requires some tuning of parameters to work well. More recently, there is this paper by Sciacchitano and company, and it is a fully automatic method, but it doesn't allow a mixed noise, that is noise that is a combination of impulse noise and Gaussian noise. Next, please. So our approach is we will take this original vector B delta and denoise it by a median filter. And this gives the vector B delta hat. And then we will apply this vector in a LP-LQ minimization method. So this is, we want to minimize the functional J of X. And mu here is a regularization parameter which determines how these two terms are balanced, the relative influence of these terms. And that parameter we will determine automatically. The P and Q have to be set by a user, and we will discuss that. Next, please. So these LP-LQ method have been developed with two Alessandros, one Buccino, right? Magnitude squared over magnitude.
Live streaming is on.
And then we also have an image here of the L.1 norm, which is a better approximation of the L0 norm. So this is our justification for using these quasi norms. Next, please. So how do we solve these problems? Well, we use a majorization minimization method. That is, we approximate the functional, which will be J, by a quadratic tangent majorant. So at our present approximate solution, which we call V, we determine a quadratic function which approximates what will be J. And so this function interpolates at V, at the current solution, and it also interpolates a gradient. Now, in order to have a gradient, the function has to be differentiable, and the function J we had is not differentiable if P or Q is smaller than 1. So therefore, we replace the J, the norms, by some kind of smooth norms, which look like this. And this results in a differentiable function. So here, in theory, epsilon has to be, it's a small positive number. In practice, we will choose epsilon to be 1, because T will be in the range between 0 and 255, and epsilon is 1 is much smaller than 255, so that it turns out to work well. Next, please. So the method is an Adm method. So one updates weights, and then one computes a new gets a new minimization problem. To update the weights, we compute the residual here. Xk is the presently available approximate solution, and then we compute some weights. Which in here these operations for computing the vectors W fid and W reg, these are meant element-wise. So then we stuff these vectors into a diagonal matrix. Next, please. And this defines our majorant. So here it is, the Q is our majorant. C is some constant which is independent of X. So what our next step then is we determine find the minimum of this problem, and that gives me my new approximate solution. That's you see on the bottom of the slide. There is an issue here, though. A is a huge matrix, and we don't really want to solve these problems because they are too large. So we will actually look for the solution only in the subspace. But first, we have to look at the normal equations, which are on the next slide. And here they are. And the only point I want to make now is that they have a unique solution, typically. I mean, because of our choice of A and L. I haven't told you about L yet, but it's an analysis operator because we will look at our solution in terms of framelets. So we will represent the image in terms of framelets. And okay, next please. So here we actually now look at the subspace. So the matrix V has many rows. Each pixel corresponds to a row, and K is the dimension of the subspace, which is not so large. And we want to solve this minimization problem, which is the same one which we saw before, but now we look for the solution in a subspace. Next, please. And the way we do this, we compute QR factorizations, and then we get a small, where Q is a tall, skinny matrix R, the R matrices RA and RL are small upper triangular matrices. So then we arrive at a least squares problem with a fairly small matrix, and we solve for Y, and then from Y we get our new approximate solution X. Next. Having the new approximate solution, we compute the residual vector for the full normal equations. And that vector then is appended to the solution subspace. So this gives a new column of the matrix V. So we call the new matrix Vk plus 1. And we can show that, yes, this method gives convergence, well, to a stationary point. We cannot really say we get a solution to the minimum because when Q and P are smaller than 1, the minimum might not be unique. And so we do get a solution to a stationary point, but in practice it works quite well. Next, please. Yeah, we can skip that. There are other solution methods for doing this. So the new part here is that we apply median filters. And so we do this by taking B delta. So B delta is the available noisy representation of my image. And we reshape B delta to get our square image or rectangular image, whatever it might be. And if the contamination is by salt and pepper noise, then we use an adaptive mean filter. I mean, this is fast. And what the adaptive median filter does is it identifies the salt and pepper grains and then replaces them by a weighted mean. So this way we get a smoother image, but it's of course not really denoised, but it's smoother than the image that has been contaminated by salt and pepper noise. Next, please. If we have impulse type noise, which is a little bit more complicated because it's impulse noise and we don't know what the value is of the noise. And there we use a directed weighted medium filter. So here are the 6 directions marked on this pixel. So say we are in the middle, and then we look at a neighborhood here. And we look at weighted medians, and we try to use those to decide if the pixel in the middle is contaminated by impulse noise or not. And if it's not, then we leave it. If it is, we replace it by a weighted median. So these filters have been around in the literature. This is nothing new we are doing. Next, please.
Yeah, we have also just 1 minute at most.
1 minute, okay. So the last minute then I will spend on talking about determining the regularization parameter. And there are a couple of ways of doing this: cross-validation, modified cross-validation. And in these methods, one removes certain parts of the data, that is some rows of the equations, and one chooses a regularization parameter so that the solution is most stable for the behaves most stable under the removal of these rows. So, but the method that actually works best and is cheapest, it's on the next slide, is generalized cross-validation, which some of you in the audience have used this method and say, well, I mean, this requires solution of a large problem, and typically it does, but we apply it only on the reduced problem we get. So when we have taken k steps, we have, instead of the two large matrices A and B, we have two small matrices of size k by k, and for those matrices we can compute the generalized cross-validation, which allows us to compute the regularization parameter fairly inexpensively. Next, please. So we can go to the next, since I'm running out of time. And here is some average noise. Next, please. And here is an image which has been contaminated by 50% of impulse noise and 1% Gaussian noise. And if we look, here's the restored image. And this works completely automatic, right? And we have another image here we can show. Well, no, we should go to the next image. Here's another image, 20% salt and pepper noise, 3% white Gaussian noise. And here is our restored image. And what the table here top tells us is that choosing Q smaller gives better restoration. So the bottom line in the table shows a peak signal to noise ratio, and roughly larger is better. So choosing Q small gives better results. It also typically means that we require more iterations. Thank you.
Thank you for the very nice talk. So we have time for a very quick question.
Hello, Alessandro. Can I ask something?
Yeah, sure, you can ask.
Yeah. Thank you very much for the talk. It was very interesting. I have just one question about the LP fidelity. So the first one is, so basically you use this LP type fidelity after having applied the median filter to your blurred and noisy image. So I was wondering if there is any statistical interpretation of this, if there is any, I don't know, sort of generalized Gaussian noise that you suppose so that it connects to this LP fidelity. And how do you choose P? Because in the results you show how you choose Q, and Q small seems good, but how do you choose the P? Oh, sorry, I didn't have my video, sorry.
No, I was running out of time here also, but the P, so I mean, if we have Gaussian noise, P equal 2 is fine.
Yeah.
And if we have other noise, then we should choose P smaller. So in these examples here, P is 0.8.
Okay.
We have used this method, we being Alessandro and I and other collaborators, have used this method in a statistical connection, and where we have applied it to a generalized Gaussian noise. And in that context, one can justify the use of P and Q using the theory. Unfortunately, when we apply the median filter, I don't know what kind of noise.
Yeah, which distribution it is. Yeah, of course. Yeah, but that's why I was wondering. Yeah.
Yeah, but in principle, one can use the theory for generalized Gaussian or for these generalized distribution, and this way justify the choice of P and Q.
Okay, thank you very much.
Thank you. Okay, sorry we don't have time for any other questions, so let's thank Lothar again. And so since this is our break, we can go on to our next speaker, which is Marco Donatelli, that will present work, again with myself, entitled Graph Laplacian in L2LQ Regularization for Image Reconstruction. So let's see if Marco can share his screen. He is non-trivial, and unmute himself at the same time.
It's okay? Do you hear me?
We can hear you.
Okay.
We don't see the screen.
Oh, very good.
But I have your slides in case. No, no,
Okay.
I see your screen. That's great.
Okay.
Perfect.
And now you hear me and you see my slide. This is right?
Yes, everything is perfect.
So I try to give this coffee break talk within in time for the end of the coffee break. And this is a joint work with Alessandro Buccini, and I will talk about the graph Laplacian that was previously introduced in the Caterina Fenu talk, and the L2-LQ regularization that was very well described. The idea is the same described by Lothar Reichel in the yearly talk, so I think that I can go quite fast. So my outline is just to introduce the model that we want to solve, that is the classical deblurring or computer tomography, so linear ill-posed problem with a Tikhonov L2-LQ regularization where we use the graph Laplacian as a regularization matrix, and so we combine the two techniques that I said before, and then we show some numerical results. So for our image reconstruction problem, we consider a data where in our case we will use the discrepancy principle, so we assume to know the noise level delta, but this is not crucial since other strategy for estimating the regularization parameter like generalized cross-validation can be applied, but okay. Well, the application that we have in mind, and I will show in the numerical results, are exactly image deblurring and computer tomography. So, as I said, we apply the Tikhonov L2-LQ regularization, where we have a regularization operator L, and we assume, of course, that the trivial intersection of the null space between our two operators A and L, and usually we know that L is a differential operator or a wavelet operator if we want to sparsify our solution, but what we use in this talk is the graph Laplacian. So we need to introduce the graph Laplacian for image. Therefore, just to fix the notation for a weighted graph, okay, we define the set of vertices and the associated weight for each edge, which is a non-negative number if the edge exists. So we have we denote by G the adjacency matrix, and in the ij position we have the weight of the edge ij, otherwise we have 0 if there is no edge. And of course, if the graph is indirect, then the matrix G is symmetric, and of course the opposite. So n, that is the number of our nodes when we okay, of course, sorry. I have to define also the graph Laplacian before to define the graph of the image. So to define the graph Laplacian, I need the diagonal matrix D, where in the diagonal entries we have the degrees of each node. And then, according to this simple formula, we can define the graph Laplacian. And as said before, since we will consider an indirect graph, the matrix L is symmetric, and we know from the theory that since it's stochastic bicolumn, that matrix, that the null space of the operator L is just the span of the constant vector. So in the Tikhonov regularization, we can reconstruct exactly the constant functions since they are not damped. So how to associate a graph to the image? if we have the image X, the nodes of the image of the graph are the pixels of the image. So the number of nodes, of course, is the number of pixels. And we define the edge for the matrix G using the same Gaussian function that was introduced by Caterina Fenu, and you can find in many imaging applications, like you can see the paper by Calatroni and collaborators and so on, where this Gaussian function, of course, decay in a fast way according to the variable, to sigma. Sorry. And we decide for the computational point of view to cut the Gaussian decay with a certain disk according to this variable capital R that decide which are the neighborhood of the pixel that are involved in the weight. So only the neighborhood at a certain distance from our pixel are weighted. For the far away pixel, we have just 0. So in practice, we have a big matrix since the size is the number of the pixel, but is a sparse matrix since we just cut a small number of neighborhood. And of course, we have to construct this graph. For many applications like image denoising, segmentation, and so on, usually we construct the graph Laplacian from the observed image. In this case, if we consider, for instance, computer tomography, of course, the observed image observed signal does not give any information. So we need a first step where we compute a first restored image that can be used as an initial guess for our graph Laplacian. So we take the simple Tikhonov problem, L2, with the first derivative as a regularization operator. So we have the gradient for the regularization term. And since we want an automatic procedure, we take alpha according to the determined by the generalized cross-validation. Okay, other strategy could be used. And for instance, if we have an image deblurring problem, this can be done by 3F fast Fourier transform. In the general case, since maybe we have a computer tomography problem, we consider a Golub-Kahn bidiagonalization with a projection in a subspace, Krylov subspace, with a classical strategy in this field that, similar to what discussed before by Lothar Reichel, we can compute the QR factorization of the matrix LV, where V span the Krylov subspace, and we look to the coefficient of our image in the Krylov subspace spanned by V. So we have just to compute the coefficient of the vector y and to solve the small size problem in the variable y. And okay, a similar strategy can be done for the GCV algorithm. You can just look at the Fenu, Reichel, and Rodriguez paper. And okay, now we have an initial approximation of our restored image that, okay, we know that with the L2 regularization, this may be too smooth, but we don't need a really accurate restoration. It's enough to have a good enough restoration to compute the graph Laplacian, such that we construct the graph Laplacian using this initial approximation x alpha, and then with the constructed graph Laplacian, we can apply the L2 LQ regularization using the majorization minimization that we have seen with Reichel. And this is done in a paper from Wang, Lanza, Morigi, Sgallari, Reichel. And okay, I don't give details on this part since we have already seen. We just to approximate, since we are interested in a non-convex functional when Q is smaller than 1. So we need a smooth approximation and to solve this smoothed minimization problem with a majorization minimization method for our quadratic functional, and we have already seen this. What I want only to stress is that we will estimate automatically the regularization parameter, okay, mu, according, or eta in this case, according to this discrepancy principle. So we change the parameter at each step, and the parameter depend on the Krylov subspace that we are spanning at the current iteration. So just an example, as I said, we take a Q small to have a non-convex functional. We take our Gaussian weight function with this parameter for sigma and for the radius of the ball, that is r equal to 10, and we compare the graph Laplacian with the first derivative operator and the frame that is okay, like wavelet in some sense approach for the L2 LQ regularization. So in this computer tomography example, we can see that we add the Gaussian noise of 1% of noise, and this is created with the IR Tools toolbox by Gazzola, Hansen, and Nagy, where our observed signal, of course, is the sinogram, and from the sinogram we want to compute the true image. So first of all, we compute the image with the L2 regularization, then we construct the graph, and then with this graph we can solve the L2 LQ regularization with the graph Laplacian. And you can see that this regularization operator with the graph Laplacian improve the restoration with respect to the classical first derivative or the frame wavelet approach. So I skip the image deburring problem, and just to conclude, not so in time for the coffee break, okay, I just stress that possible, of course, as Lothar Reichel showed in the previous talk, we could go in the direction to consider also the LP norm for the data fitting term, and in the computer tomography application, of course, it will be crucial also to add the non-negativity constraint. Thank you very much for your attention.
Thank you, Marco. So we have time for a telegraphic question if someone has one.
I have one. So you said that you use the discrepancy principle. What if you don't have an estimation of the value of the noise?
Okay, nice question. Also, I'm lucky to say that we did also the version with the GCV method. Since I didn't stress yearly, but since we used your approach for the computation of the first approximation X alpha, in a similar way, following your idea, also in the graph Laplacian, here we could replace the discrepancy principle with the GCV. And it can be done, it works, and in the paper, I didn't show in the slide, but you can find some details in this direction in the paper. So yes, we again use your strategy. Thank you very much for that.
Okay, thank you for your answer.
Okay, I'm sorry to cut off, but we don't have any more time, so we can just power through. And we have the first talk of the next session, which we are already way late off for, which is Luca Calatroni's talk.
Hello, can you hear me?
Luca. Yes, we can hear you.
So let's try
and we
share.
can see the slides.
So let me go full screen. Wait, do you see?
You can see it full screen, yes, perfect.
Yeah.
So this is a joint work with Simone Rebegoldi, and it's entitled Scaled Inexact and Adaptive Fast Iterative Soft Thresholding Algorithm for Convex Image Restoration. Thank you, Luca, the floor is yours.
Thank you very much. So I'm happy to be here, although virtually, and despite the organization roller coasters, I'm happy that there is some exchange in this conference, in this workshop. So thanks a lot for organizing this. So yeah, I'll be presenting you some recent work I did in collaboration with Simone Rebegoldi. In particular, it's some sort of specified result of some more general results that we obtained in an extended version of this paper. But here, the point. Stopped. So how to develop fast optimization algorithms for solving a composite optimization problem. So since the time is short, I just set up the scene very shortly. We are interested in solving a composite optimization problem of this form. So we want to minimize a convex functional, which is the sum of two terms. The first one is supposed to be a C1 smooth with a LF Lipschitz gradient, whereas the second one is a non-smooth term. And we will access to this term through the calculation of its proximal operator, which is defined in this form. So clearly the joint functional then is a non-smooth due to the presence of G. So standard gradient descent optimization methods cannot be applied. But what is pretty standard nowadays is to use what is called forward-backward splitting algorithm, or also called proximal algorithm, where the idea is that you do perform a sort of gradient descent iteration using the smooth component, so using your F component, and then implicitly somehow you evaluate your non-smooth component, G, through the evaluation of the proximal point. Note that since G is convex, this function that you want to minimize to compute the proximal point is strictly convex, so this is well defined and is unique. So it can be found in general references that the speed of convergence in function values of these time stepping is as slow as the one of gradient descent. So in particular is of the order of 1/k, where k is the number of iterations. So standard approaches to improve upon the speed of convergence include inertial methods. And one very popular one nowadays is the approach that is dubbed FISTA, which stands for Fast Iterative Soft Thresholding Algorithm. The idea is that instead of moving along the standard trajectory of your proximal algorithm, you somehow introduce inertia, which has to be understood in the following. Basically, you define a direction in terms of the iterates xk and xk minus 1. So you define this direction, and then you define an extrapolated point, which doesn't need to lie in the trajectory of your iterates. So here is called yk plus 1. And on this point, you apply your time stepping. So basically, the idea is how to define these this extrapolated point in a suitable way, and there are some standard rules for that. So in the case of smooth optimization, so for accelerated gradient descent, some previous work was done by Nesterov, and it can be sort of easily extended to the case of non-smooth optimization. So basically, through some explicit computation of your extrapolated points, what you can get is an improved convergence result, where now your speed of convergence in function values is of the order of 1/k square, which is faster. So what are the issues of like FISTA? So many of you maybe have used it in the standard form, where you combine, I don't know, L2 data fidelity with L1 sparsity promoting regularization, and it's sort of an easy case. But there are more complicated situations, for instance, when you deal with more complex sparsity promotive regularizations where some issues may arise. So the first one is that in these convergence results, what I'm showing here is a sort of uniform bound on the time step tau of your algorithm. So it's the sort of time step of your gradient descent, which appear also here, which depends on the inverse of your Lipschitz constant associated to the gradient of f. About the fact that you are computing proximal points. So those are solutions of optimization algorithms. So if you are lucky, you can imagine to find like an explicit and a closed form expression, but very often this is not the case. Think, for instance, of having a total variation regularization, then you cannot compute the proximal point in closed form. And then also, can we make somehow the convergence faster by including some sort of scaling, non-Euclidean scaling, in agreement with the classical theory of scaled gradient descent methods, so that they resemble a little bit like Newton type updates. So about the adaptive backtracking that we introduced, the idea was the following. So standard approaches covering update of the time steps are typically monotone. They rely on a sort of Armio type line search. So in particular, you start from a reasonably large time step, and you refine these along the iterations. The problem is that whenever you start with a bad estimation of your Lipschitz constant, then it corresponds to have a very small estimates of your time step. And since the strategy is by definition monotone, you cannot improve it anymore. So we decided to use some adaptive backtracking strategy, which was proposed in the convex case in this work, and where I previously worked in strongly convex scenarios with some linear convergence results. And about inexactness, as I mentioned before, very often to compute proximal points, you need to solve inner optimization problems. And in the original paper by Beck and Teboul, where they applied FISTA to TV deblurring problems, so TV plus L2 fidelity with an operator, they observed that whenever the inner proximal problem is solved with like a fixed number of iterations, for instance, here is 1, 2, and 5 inner iterations. If the number of iterations is too small, so if you solve it in a very inaccurate way, then your global convergence may be affected. So the idea is to control somehow the errors along the iterations. And about the scaling, the idea is to get inspired by some previous work in the context of smooth optimization. So in particular, the framework of scaled gradient approaches, and introduce some non-Euclidean variable metric updates, where, without going into the details, the fact is that you redefine your proximal operator by substituting, instead of a Euclidean norm here, a scaled version of it, where basically you have dependence on a symmetric and positive definite matrix, which defines a little bit the sort of data-dependent matrix that you want to use to improve convergence speed. And there are some conditions that, of course, I don't have time to detail here, but the idea is that in your algorithm, what you want to do is to define something like an Hessian matrix, which squeezes towards the identity along the iterations of your algorithm, so that in the early iterations of your algorithms, you do benefit of some second-order update, let's say, without, let's say, requiring too high computational costs. And as iterations number increases, then your matrix converges to the identity. So you retrieve standard first optimization scheme. So let me just show you the main sort of tool that we use to prove our convergence results. So this is the standard version of the descent lemma that combines with different color codes the different ingredients I've mentioned so far. So inexactness is encoded here in terms of some errors that accumulate when you iterate this equality. The scaling appears here in the sort of non-Euclidean norms that you have here, and adaptivity appears in the calculation of whatever is orange in this slide. And in particular, this bracket is defined in terms of the Bregman distance associated to f, which is typically non-negative, so you can forget about this term when you enforce recursion in this inequality. Whenever you fix a time step that is constant and smaller than 1 over your Lipschitz constant Lf, but this equality can be also be checked on the fly, so that you can allow local updates. as I said before, you also have non-Euclidean quantities, and you have here some inexactness terms that depend on some definition of inexact calculation of proximal points that is a little bit technical, so unfortunately I don't have time to go over it now. So this is the new algorithm, where basically you have some backtracking parameters that control at each outer iteration some tentative increasing step size and the following possible adjustment. So it looks very much like Vista, as you can see here, apart from some different updates. So basically at each outer iteration, you try to increase your step size, and then you do like a standard Armio backtracking check, which ends whenever your condition on the Bregman distance is verified. So inexactness is enforced here, so whenever you calculate your proximal points. So without going into the technical details of the requirements, you need some ability conditions on the errors that are introduced along your iterations in order to have them controlled in the estimation of your convergence speed, so that you can prove that for this scaled, inexact, and adaptive algorithm, you still have the same speed of convergence of Vista. But the advantage is that compared to the non-scaled variant, this is supposed to be much more effective. And you can find the proof and like more details also to the strongly convex case in this paper. I just conclude with a very quick application showing you the performance of this algorithm. The inverse problems we have in mind, the problem of Gaussian deblurring. So we have an observed data, Gaussian deblurring with Poisson noise. So we have a noisy and blurred version of my ideal image X, which is here called Z, which is the effect of a degradation process, which is the composition of like some Gaussian blur, some constant background, for instance, and some Poisson degradation model. So as a data fidelity, then the appropriate choice is the Kullback-Leibler divergence between AX plus B and the measurement Z. And we need to choose some sparsity promoting regularization term. So yeah, I skipped that. So what we decided to use is like a discrete form of the total variation with a non-negativity constraint, so that the composite model that we deal with is the following. Here we have the smooth component, and here we have the non-smooth one. Basically, we apply our algorithm to solve the blurring problem to this type of images where you have Poisson noise and Gaussian blur for some fixed background. And let me comment that here the estimation of the ellipsis constant is typically very bad due to the fact that at the denominator you have a b squared term, and in case when this is very small, then it makes the estimation very large, so your step length is typically very small. So having some backtracking here is really beneficial. So those are the sort of convergence rate result. On the first row, you see the result that we obtained using standard monotone backtracking. And in particular, you see in blue the convergence speed of standard Vista, so where no scaling and no inexactness is kept into account, whereas whatever is below is the convergence speed of like scaled version of Vista with appropriate choice of the scaling parameter. So you see that you can do much better. And in particular, introduce also what is in the second row. You do have better results. So the difference here is that you're using adaptive backtracking. So this plot concerns the rates along the number of iterations, and these along the computational time. So in a reasonable computational time, you can get very, very good results. And here is much more interesting to see the comparison between non-scaled version of Vista with standard monotone backtracking, its adaptive variant, and then the corresponding convergence plots when you have scaling involved. And here, just to conclude, you have an estimate of the Lipschitz constant. So for monotone type backtracking, since your time step gets updated in a monotone, non-increasing way, on the contrary, your Lipschitz constant estimates gets updated in a monotone non-decreasing way. So that's why you see this solid pink line that stays constant, whereas when you have adaptivity included, then your Lipschitz constants get smaller and then your time step gets bigger. So that's why you still do better when you combine the scaling with the adaptive backtracking. So to conclude, we propose basically an extension of the FISTA algorithm, which combines several features. In particular, it combines non-Euclidean scaling to encode some second-order information. It includes some adaptive backtracking to mitigate possible misspecification of initial step sizes, and it covers a precise convergence analysis that takes into account the presence of errors in my computation of proximal points. So it's suited for a large variety of convex and strongly convex optimization problems. So we have like a more theoretical paper that is then the second round of revision now, and we have some more applied paper where we applied this SPSTA to some super resolution problems similar to the ones that Claudio described in his presentation. And now the idea is to use this scheme as an inner solver also for non-convex optimization scenarios, for instance, such as majorize, minimize schemes in order to improve the global convergence speed. So thank you very much for your attention.
Thank you, Luca. We have time for a very quick questions. Question one.
Yeah, I didn't have my video, I'm sorry. Yeah.
No questions for Luca? Okay. Okay, so we can move on. Thanks again for this nice presentation.
Thank you.
And the next speaker is Federica Pes from the University of Cagliari. She will present a work in collaboration with Patricia Diaz de Alba, Luisa Fermo, and Giuseppe Rodriguez. The title is Minimal Norm RKHS Solution of an Integral Model in Geoelectromagnetism. So, thank you, Federica.
Can you hear me?
Yes, we can see your slides. Thank you.
Okay, thank you, Caterina and Alessandro, for the invitation. And in this presentation, I'll talk about a numerical inversion of an integral model involved in applied geophysics. This is a joint work with Patricia Diaz de Alba from the Gran Sasso Science Institute and with Luisa Fermo and Giuseppe Rodriguez from the University of Cagliari. Our aim is to reconstruct some soil properties, in particular the electrical conductivity of the soil. We denote the electrical conductivity as a function of depth, sigma z. The main device used is a ground conductivity meter. It's composed of two coils, the transmitter and the receiver. The transmitter produces primary electromagnetic field. In the picture is represented by the green lines. And the receiver senses a secondary magnetic field produced by the soil. About the instrument, there are some parameters that can be varied in order to get more data. These parameters are the orientation of the coils, because can be used in vertical or horizontal orientation, the height over the ground, the angular frequency, and the distance between the two coils. Here we present the mathematical model that describes the interaction between the device and the soil. It's a linear model composed of two integral equations of the first kind. The first equation corresponds to the vertical orientation of the coils, while the second one corresponds to the horizontal orientation. Our unknown is the function sigma. Kv and kh are the kernel functions, and the right-hand side, Jv and gh, are the apparent represent the apparent conductivity of the soil. In this presentation and in this work, we only focus on the first equation. And we assume that at a sufficient depth Z0, the electrical conductivity stabilizes and converges to a value beta. This assumption allows us to decompose the original model, decompose the integral in the sums, and we can estimate the last integral by this quantity. So our model becomes of this form. Obviously, in application, the right-hand side is discretized. So we have to solve this integral equation with discrete data. There is an issue because this problem has infinitely many solutions. Among all the infinitely many solutions, we search a function sigma that minimizes this quantity. So we search a sigma for which is minimal the second derivative of the function. Here we need to introduce this linear function, gamma, because we search a solution in particular Hilbert space for which the value at the endpoints of the integral are equal to 0. So we introduce this gamma, we consider the difference sigma minus gamma, and we obtain this model. So first of all, we search a function phi for which the value at the endpoints are equal to 0. In this slide, we record some basic properties of functional analysis. We consider the space, the Hilbert space L2, with this inner product and this induced norm. And we consider the subspace W, composed of function square integrable functions with homogeneous boundary condition, and the first derivative is absolutely continuous function, and the second derivative is a square integrable function. In this space, the inner product is defined in this way. So considering the inner product between the second derivative in the space L2. And the induced norm is also the induced norm is defined by the norm of the second derivative. We remark here that the space W is a reproducing kernel Hilbert space that is the SXF function G, satisfying these two properties. The function G is a function belonging to the space W, and any function F can be written as this inner product. We denoted by Kn the bounded linear function defined in the space W, and we would to solve this minimal norm least squares problem. According to the Riesz representation theorem, any function belonging to the space W, for any function exist functions known as Riesz representer at I, for which is such that is verified this relation. We introduce the null space of K and its orthogonal complement. Can be proved that the orthogonal complement is spanned by the Riesz representers. So we can write the minimal norm solution as a linear combination of this Riesz representer. After some computation, we get this linear system, GC equal phi, in which the coefficient matrix G, each component, is defined by this inner product, the inner product between the risk representatives. We need to have the expression of the second derivative of the functions eta and the expression of the function eta. After some computation, we get that the second derivative and the functions eta are given by these integrals. Here we reported on the left the function, the second derivative, on the right, the risk representatives eta. We can see that in this case are smooth functions. Obviously, in application, the exact data are contaminated by a noise vector. We need to regularize the problem. First of all, we write the matrix G in terms of its spectral factorization, U lambda U transpose. And we consider the truncated high decomposition solution with a regularization parameter K. So the take solution of the original problem is given by this sum, in which this gamma, this function gamma is a linear function introduced before. Now we illustrate some numerical example. We add the Gaussian noise to the exact data, where epsilon represents the noise level. We estimated the regularization parameter in different ways. We denoted the best regularization parameter, the parameter in correspondence to the minimal norm error with respect to the exact solution. Then we estimate K by the discrepancy principle, and finally with the L-curve criterion. As a first example, we consider this smooth function. In the picture on the left, we reported the reconstruction without noise, but without noise means that are present only rounding errors of the order 10 to the power minus 16, and the reconstruction is very accurate. On the right, we add very small noise level, and we can see the instability of the solution. So we need to regularize the problem. And here we reported the regularized solution, the take solution. On the left, we consider 3 different values for n, the size of the vector data. And on the right, we reported the solution corresponding to the 3 different type of ways to estimate the regularization parameter K. Here we have a second example. We can see that in this point in which the function is non-differentiable, the reconstruction is not very accurate, but anyway, the maximum is located. As a last example, we consider this non-continuous function, and as a previous example, the reconstruction is not accurate, but the maximum is recognized. On the left, we reported the reconstruction by applying 3 different values for the noise level. On the right, we reported the reconstruction by using the three different ways to estimate the parameter k. And with this, I ended my presentation.
Thank you, Federica, for this nice presentation. So we have time for questions.
I have just it's more of a curiosity than a question. On slide 4, you have a minimization problem. Sorry, slide 5. Yeah. So you want to find, here you say a function such that minimizes the second derivative. Is this unique, or it's no way, or there is multiple solution here?
There is multiple solution, and so for this reason, we must introduce this base W.
Okay, I see. Thank you very much.
Thank you.
Fede, I have a question too. You used zeta 0 equal to 4.
Yes.
How does the result change when you use another value? Let's say I don't know anything about the model. I overestimate that. I'm sure that with zeta 0 equal 100, I have a good value for beta, let's say.
Zeta, we fixed zeta z0 equal to 4, because after this value, the function sigma stabilized to a value. So we truncated in the integral in this point.
Okay, but did you try to put another value? How does the results change in that case?
No, I tried only zeta 0 equal to 4.
Okay, it was just a curiosity. Thank you.
Thank you.
Okay, so thanks, Federica, again for the very interesting presentation. So we have one last talk. The speaker is Jianglan Bai. Sorry if I misspelled that. Who is presenting a work in collaboration with Alessandro Buccini and Lothar Reichel. The title is Solution of Linear Discrete Ill-Pose Problems by Discretized Chebyshev Expansion. So, as Alessandro said, the floor is yours.
Okay, thank you. Okay, so my slides are showing.
Yes.
Okay. So what I present is a method, what we call is a Chebyshev method for inverse problem. So it's based on a solution subspace that consists of discretized Chebyshev polynomials. Okay, so first I will have a break, introduce some background of the problems that we are concerned, and then I will introduce the Chebyshev method that we propose, and then briefly go over the methods that we compare the Chebyshev methods with in the later computed examples, and then the conclusion. So first, we are concerned about the inverse problem. So the linear system stems from integral equation, ill-posed integral equation, and then a lot of time we solve a least square problem instead. And because the observed data is usually contaminated, and because the matrix A is ill-conditioned, so we need to regularize it. And what we are the problem that we are actually solving is the regularized problem, 1.5, the Tikhonov minimized problem. And then I will introduce the Chebyshev methods. So PSL denotes the orthogonal projector onto the subspace SL, and when SL is a suitable subspace, the approximation of A, the projector times A, is a good approximation of A, and of course it requires L to be big enough so that the singular value of A is small enough so that it's a good enough approximation. And then what we are trying to do is that we are trying to define this subspace SL by discretizing Chebyshev polynomial first kind. So basically cosine J theta. This is how it's defined. And to do so, first we need to introduce the Chebyshev matrix W. So W is defined like this. So basically this is a normalized discretized Chebyshev polynomial discretized at the Chebyshev points, or other words, zeros. And then WL times WL transpose would be the orthogonal projector onto the range of this Chebyshev matrix WL. So the first method we propose is very straightforward. So we replace matrix A by WL transpose A, which is basically orthogonal projector onto the range of WL times A. And then after a substitution of approximated solution X and some simple simplification, QR factorization, we arrived at a low dimensional minimized problem, which costs much less to be solved. And also we proved this theorem. So what this theorem says is basically when the kernel of the integral equation is smoother than the approximation of this A by this projector times A is better. So basically Chebyshev methods works better on the more analytical functions. And then this second method. So this method starts from the discretizing the integral equation. So we with a change of variable, and we have an integral equation that satisfies the theorem we previously proved. And then we discretize this integral equation at with the midpoint composite midpoint rule at the Chebyshev points, at the zeros of Chebyshev polynomial. Sorry. We use the Chebyshev matrix just like we defined previously, and we call this method Chebyshev projection method because we apply the A matrix on this Chebyshev matrix, and then we compute a QR factorization, and instead of the Chebyshev matrix W, we use the Q matrix as the Q matrix, and we use the QQ transpose as our orthogonal projector, as we can see later. So we compute a small S3D, and then the QQ transpose A is our approximation of A matrix. And this minimized problem is equivalent to this simplified minimized problem, and with a substitution of approximated solution and the QR factorization, and we arrived at this low dimensional minimized problem 2.12. And this is for the case when m is bigger or equal to n. And when m is smaller than n, it's slightly different, but still very similar. So instead of AW, we apply W transpose to A, and then we compute the QR factorization of the transpose of the product. And then we proceed just as previously. Everything is very similar. And then we compare the Chebyshev methods with randomized method and Krylov method. So random methods, as we said, is very similar to the third Chebyshev projection method. Instead of the Chebyshev matrix, we had this omega matrix, which is a random matrix. The entrants are identically normally distributed with 0 mean and variance 1. And the method itself is very similar to the Chebyshev projection methods. And then the Krylov method we compare with this method based on Galois-Kahan bidiagonalization. So after L steps of iterations, we can get this VL matrix, the range of which is a Krylov subspace. And with the relation 3.11, we minimize the Tikhonov regularization problem on the Krylov subspace instead. And with the substitute of the solution X, and with the relation 3.11, we arrived at this simplified and minimized problem. And then the computed examples. So we test the Chebyshev methods on 4 different problems. So the BART, Schorn, Blur, and BART2D. So the BART and Schorn are one-dimensional, and Blur is a 2-dimensional problem, and BART2D is a problem that we constructed. So it's basically a canonical product of the 1D BART problem. It's constructed this way. And this is the notation we use in our table. So this is the result. So as we can see in BART and Schorn, so basically the 1D problems, the Chebyshev methods works very good. So this first table is the relative error. And then we have a table for time too. So as we can see, the Chebyshev methods works very good on the BART and Schorn, and but on the Blur problem, the 2-dimensional problems, the Krylov method works much better than both random and Chebyshev. So actually on the problems that so BART2D is also a 2-dimensional problem, but Chebyshev methods works okay, and random also works okay on this problem. This is because for the previous 2 1D problem, the singular values of the problem decrease very rapidly, so the problem has only few significant singular values. But for the Blur problem, the singular values decrease slowly, and it has more significant singular values. And on this type of problems, we found that random methods and Chebyshev methods doesn't work so well. And also one thing, one thing we noticed about this Chebyshev methods, one different the Chebyshev from the random is that the Chebyshev method, the subspace cannot be too large. That is because the Chebyshev polynomials with a bigger index, it will oscillate more and will have a higher frequency, and that is not a good feature that we want to approximate a solution. So as we can see, when the size of the subspace L increases, the random methods, the accuracy of random method increases. But for the Chebyshev methods, it didn't really increase a lot. Basically, stays almost the same. And then the timing. So the Chebyshev methods has a advantage on timing though the accuracy is a little bit lower on the Blur problem, but the timing is still very competitive. So basically Chebyshev methods behaves like the randomized method, but it's competitive on the problem types that random methods are good at, but also it has the same drawback as the randomized method. It doesn't work so well on the 2-dimensional problem. So that's all. Thank you.
Thanks. we have time for a quick question. I have a curiosity. Did you try to use Fourier basis instead of Chebyshev?
Excuse me.
Can you hear me?
Yes. Can you repeat? I didn't hear very clearly.
Did you try to use the Fourier basis instead of Chebyshev one?
Oh, you mean the Chebyshev of type 2? We use the Chebyshev polynomial of the first kind. Yeah, and we didn't really try the other type of Chebyshev.
Okay, thank you. Thank you again, and we would like to thank all the speakers for these two last sessions. Thanks for accepting our invitation, and that's all.
Yeah.
Hello. Hello. I have any question?
Oh, yeah.
Yeah.
Yes. I'm sorry to interrupt you guys.
We cannot see you.
Yes, I will make the video.
Okay.
Hello, you can see me?
Yes, now yes.
Yes.
All right. Dr. Osvaldo rescheduled me to session 16 room E to introduce my presentation. Actually, I should introduce my presentation this morning. I'm in South Korea, but I got some issues, so I couldn't do it this morning because of internet. So he told me to come here and to present my paper. So this morning, my session was 16G, and the chair was Katarina Finu, and then the technical assistant.
Okay,
Yes.
you are Joao Biocco or something like that?
Yes, I've sent the email, and then
yeah. But this is a workshop. It's different from general track, so you cannot do your talk now because it's a different thing. I was the chair this morning, but this is a different workshop.
Yes, so like 1 hour. So Dr. Osvaldo he sent me message and he told me to come here and introduce it. So is it impossible?
But who told you to come here?
Dr. Osvaldo.
Sì.
Just one moment.
Just one moment that we figure this thing out.
Thank you. Please, I need your favor to present my paper. Even 10 minutes is enough.
Tomorrow morning. This is Osvaldo Sept Session.
Prova a cercare il suo nome. Spegni il microfono per favore un attimo.
Okay, so we were trying to figure this out. So let me try to do something.
Oh,
Okay, so in this way you can see us and we can see you.
okay.
So you were supposed to talk, right, in session 14G, right? First talk.
13.
1-4.
13G. The time this morning, I think it's at 10:50 or 45 this morning.
So it's, sorry, so it's this one.
All right, all right.
Who told you
I
that?
was-
Who moved you to this session? Because the next one is beginning in a few moments.
I was connected. I saw you guys when it was presented another one, and then I watched it on the YouTube, but I got problem to connect on the JITS room. Sorry. So I've sent a several message to the organizer, and then Osvaldo doctor he told me to came here and they introduced quickly. So that's why I'm here, guys.
Maybe if you have time, write an email to Professor Gervasi and ask him if you can present tomorrow morning in a session where the chairman is Osvaldo. Because now we not have time.
Okay, so
Your session was this morning.
yes, of course.
And why you don't pretend in this morning?
Yes,
Now
this
we
morning.
don't have time.
This morning I was connected. I saw you guys presented, but I cannot join the line because of the guest. I have some problem in my located. I'm in the South Korea. So I would like to connect it, but I have some problems, and now the problem is try to fix. I sent the message to him. He just answered me 1 hour left. He said, I reschedule you to the session 16 room A. So be in the room at the, like he said, 4:50.
Hear me. In this morning, your room was room G, not room E. Now the first session is not general track, but another session, and we don't have time to hear your presentation. For this reason, I suggest you to write an email of Professor Gervasi in order to ask him if you tomorrow in the morning, in the Italian time, you will try to expose your work, because in this moment it's impossible. In a few minutes we'll start another session, and I don't have time, because in this session maybe are 5 related, and we must close at 7 o'clock. So we don't have time now. I'm sorry.
All right. So you told me, I got the point. So you told me to write the email to whom? Can you send me the email?
Yeah, we can write it on chat.
On chat.
Ok. Provo a chiamare Ivan, così poi chiedo.
Intanto noi mettiamo qua nella chat quello di Gervasi, cos'è?
General Track dovrebbe essere.
No, la mail di Gervasi.
Ah, non la conosco.
Ah, ok. Ah, grazie. So we will write to you the email of Professor Gervasi so you can talk with him.
Appunto Gervasi.
Quindi Osvaldo.
Is it Osvaldo?
Yes.
Yes, but he's Osvaldo. I'm talking to him now.
Gervasi.
He is the one. He's the one who introduced me. He told me to came here.
Then I
will send you the email again.
Yeah, you need to talk with him because it's
exactly, man.
It's impossible that it said to you to come here because it's a different thing. You need to speak in a general track session. This is a different thing, okay? And we don't have time. At 5:30, another session is starting, so you cannot speak here. Okay?
Okay.
Okay.
I got the point.
Yes.
Thank you.
And we are sorry.
Okay, no problem.
Okay. Bye-bye.
All right. So
All right.
thank you, everybody, and sorry for the the various events of today, which were kind of interesting. But okay, we got to the end, which somehow sounds like a miracle.
Well, thank you, both of you, for
thank you for coming and to bear with us.
Yeah, thank you.
And that was the easy part. I computer problems and this and that. I still don't know why I wasn't able to show my slides, but
Oh well, that's not a problem.
it doesn't matter anymore.
So now we all deserve a big beer, and we will have to leave the floor to the next session. Yeah. Oh yeah, we appreciate the T-shirt, Lothar. All right.
So wish I was there.
Me too.
All right.
Okay. See you.
See you
again.
all soon. Hopefully in presence.
Yeah.
Bye.
Bye,
Well,
Alessandro.
have a good evening. I will go and teach.
Oh, have fun, Lothar. Bye, everybody.
Bye-bye.
Bye. Thank you.
Hello, hi everybody. Alessandro is speaking. Costantini, which is the chair of this session, which is AMDA. And just to tell you that I'm here just to see if there is someone of the speaker connected and try the connection or even the sharing. For example, I see Paolo. Hi, Paolo, can you hear me?
I can hear you perfectly.
Okay. Also, can you speak again, please, just to set the audio for our side?
Okay.
Okay. Yes. I can hear you fluently. Yes. Perfect. Can you try to share, as you are also the first presenter, just to see if everything works? Otherwise, I have your presentation and I share it for you if needed.
I'll try it. So are you seeing it?
Yes, we can see a comparison of anomaly detection method for industrial screw targeting. Yes, it's okay. Fantastic. Thank you, Paolo. You can stop sharing.
Do I need to move to full screen, or do you see it in the full?
As you like. From my side, both in the screen and in the monitor, I can easily see your presentation.
Okay.
So at the end, it's up to you.
Okay. Probably I'll go to full screen. But okay, I will stop sharing.
Perfect. Thank you, Paolo.
Okay.
Then we can wait for the other as soon as they appear. Cecilia, hi Cecilia, Alessandro speaking for this session. Are you there?
Hi, good afternoon.
Hi Cecilia. So as I asked you the same thing of Paolo, if you like to try to share your video and see if everything is okay.
Okay. Can you see it?
Okay. Yes.
Is it okay?
Yes, it is okay. Object detection with retina net on aerial imaginary. Okay, perfect. I can see. Thank you, Cecilia.
Thank you.
Bisogno di prendere il tuo account e di dire share, giusto? And so for you in connected, can you see the presentation? A cloud edge orchestration platform.
Are you here, House?
No, I think no, condividi schermo. Ok, so just share the screen, share, and here. Can you see the sharing? Good, I hope so.
Oh, okay. Attiva la fotocamera.
Cosa?
Accanto al microfono.
Ok.
Prova adesso a condividere lo schermo.
Ma è già condiviso. This is still shared.
Prova a vedere la presentazione.
Because look, if I go here, they should be from remote. They should see the presentation. Paolo, Cecilia, can one of you confirm that you are able to see this presentation?
Yes.
Fantastic. Thank you. Then I can also stop sharing for the moment. Just wait the other. We are waiting for Elisabetta and we are waiting for Tasni. And then, okay, we have at least other 5 minutes before starting. Okay, Tasni, I can see you. And can you hear me? You are muted. Now it's muted here.
Okay, but in a few cases, it's a problem of the emission. So click.
Oops.
Ok.
Come si toglie questo, no?
Ok. Clicca qui sui 3 puntini.
Sì.
Autorizza moderatore. Sì. Ok.
Sei sicuro?
Sì.
Aspetta, perché qui...
Perché non a tutti cioè qualcuno potrebbe avere problemi con...
ma questo qui lui...
Anche
vedi, il partecipante ha il microfono spento.
Ok, c'è qualcosa scritto in chat che non vedo?
I can hear you. Okay, Tasnim, fantastic, but we cannot hear you. Basically, just open the mic and try to speak at least.
Hi.
Okay, here you are.
Yeah, I'm here. Hi, how are you?
Fine, thanks. So, Tasnim, can you try to share your presentation just to see
Sure.
if everything is good or if there are some problem?
Yes, sure. So share your screen. I'm sharing.
Yes, I can see.
Okay, perfect.
Perfect. Thank you, Tasnim.
You are welcome.
You can stop sharing.
Okay, sure. So everything is okay.
For my side, yes.
And for my side is yes. Also.
Perfect. Thank you.
You are welcome. So I will mute myself.
Perfect. So I think you have just Elisabetta missing at this point. Okay. At least other 2 minutes. Hi everybody, thank you to be connected. I'm Alessandro Costantini from INFN, the National Institute of Nuclear Physics here in Italy, where the conference ICCSA is taking place. And I'm the chair of this session that is the AMDA workshop, and we are trying to, let's say, sharing knowledge and understanding in terms of machine learning approaches and suitable for, let's say, for industrial and for these such activities. Starting from the agenda, the first presenter is Paulo Cortez. Paulo is here. So here and the title, please, Paulo, can you share
sure.
the presentation?
Sure.
Perfect. Okay, we can see your presentation, and the president Paolo is going to tell us about a comparison of anomaly detection method for industrial skew fingerprint. So, Paolo, the floor is yours, and I remember to you and to all the participants that you have 15 minutes in total, and I will let's say stop you at 2 minutes from the end. So, please.
Okay. Okay, good afternoon. I'm presenting the paper, A Comparison of Anomaly Detection Methods for Industrial Screw Tightening. This is a joint work between the academia and an industry, which is Bosch, and it's involving a real R&D project. I myself, I am an associate professor at the University of Minho. Right now I'm talking from Portugal. Through the internet. And in the last decades, I've been working a lot with artificial intelligence applications to the real world and how to show impact in terms of decision support. If you want to know more, you can check my webpage. Turning on to the motivation. So this piece of work is inserted within the revolution of the Industry 4.0. The idea is to put a lot of sensors in the productivity systems of the industry, trying to collect digitally all this data and then trying to analyze it by using business analytics. There are huge opportunities in this area. There are many things that can be done, but this work in particular works with handheld screwdrivers, which are often used in the Bosch company because it's an electronics assembly company. And these handheld drivers, they are kind of automated systems, but that work with a human operator. And after finishing the screw cycle, the operator needs an immediate response to know if the screw was correct or not. And currently, the company uses a very simple, rather static system that is based on sum defect catalogs. And so it has a collection of sum defects. And if the way the data is generated follows the typical curve of a data catalog, it is signaled as a failure. The idea is to see in this study if we can automate this process and turn it to something more flexible and automated, and possibly with better results if we use machine learning. In terms of industrial data, each time there is a screw tightening, there are hundreds of values that are generated. Typically, the most common values are the angle and the torque, and this generates around 400 values per fastening cycle. It depends on the fastening cycle, but other values are computed, like the gradient. The fastening cycle is also divided into 4 main steps, and each step, the step number and the total angle, total torque is also recorded. And then there are other variables that are collected for each fastening cycle, like the energy. In this work, we initially worked with all these variables, but the models were too complex, and there was a huge number of examples to train the models. It's big data. So we decided to simplify the process, and actually we received much better results, which I'm going to show. The final variable that is here is the screw gov, which we use as the gold standard, and actually is the response given by the data catalog system. But it's the only labeled data that we can have access to. So that's why we use it as the gold standard. So this image shows a typical curve of a good screw tightening. You can see that there's a kind of a step zero that leads to negative angle. But basically, this means that the screwdriver is turning backwards to catch the screw. And then it starts with this red, which is step 1, and then proceeds to step 2, 3, 4, and so on. And this is an example of a screw that was good. One interesting property is that the angle can be seen in almost all cases as a time variable, because every time the angle increases, this means that the fastening is evolving further. So that's why the simple approach that we are using actually works. So we just worked with 2 days of screw tightening processes, which were collected in 2020. But these 2 days, they correspond to around 3 million of records. And they are related with 6,000 fastening, around 6,000 fastening cycles. One particularity of this problem, which is typical in quality domains, industrial quality, is that actually the data is highly unbalanced, meaning that in most cases the fastening cycles are okay, and only in a very small, tiny amount of cases there are failures. In our data set, in this 6,000, we only have 74 defects, which corresponds to 2% of the data. So this is a challenging thing for the learning models. The target and the main goal of this paper was to model what we call the first goal, which basically is at the end of collecting the data of a fastening cycle to detect if there's a failure or not. But there's a secondary goal that we roughly signal in this paper, but in the future we'll try to inspect it more carefully, is if a fastening cycle is detected as a failure, we wish to provide additional information to the human operator, meaning to identify where did the failure took place and why. Our approach is very simple. We only use two numeric inputs, the angle and the torque. This means that the models are faster to train and they provided very good results. In most cases, we work with one class unsupervised learning methods. Why? Because they are much easier to use. This means that they don't need to work with labeled data. We assume that the training data only includes normal cases. There's no need for labeling. And we used LOF, which is a standard statistic technique for anomaly detection, isolation forest, and a deep autoencoder. As a baseline comparison, we also tested the random forest, which is a supervised binary classification method. This image shows a view of the autoencoder, which only considers two inputs, and in the middle has a latent state with only one neuron, which squeezes the input signal. And the idea is to train this network to output the same input value, meaning that it can learn to compress the signal. And the idea is that if we have new instances, if the signal is similar to what it has learned before, it will produce a small error. If the error is high, we can assume that it's anomaly. So we can measure this as a degree of anomaly, which can be considered as a probability if we normalize it within 0 and 1. And if we need to signal a label, we simply define a threshold. So we did what we assume a very robust evaluation, meaning that we applied the rolling window procedure. This procedure was set in a way that the models are trained 20 times. So we train the 20 times. We do 20 executions of all the compared models through time. In each execution, there's a amount of the oldest data is considered for training, which we signal here as W, and then we provide we try to estimate the value of the learning model by testing it on unseen data. And in this case, unseen data means 500 fastening cycles. We slide it through time, and this allows us to do a very realistic execution. At the end, we aggregate the evaluation metrics that we compute. We use the ROC curve, which is quite known for binary classification tasks. We compute the area of this ROC curve, and then we compute the average, the median values. And we also store the computational effort in terms of training and testing, because this is relevant in this domain. This table shows the most relevant results. So it aggregates everything that I have spoken before about the rolling window. And basically what it shows is that LOF produces the worst results. The other methods behave much better. The best performing method is the isolation forest, which provides 99% of correctnesses in terms of the median LC and the average LC value. The only catch is that it requires a higher training time. One of the autoencoders that we use, that we call reuse, and it's reused because instead of using random weights on every iteration of the rolling window, we reuse the previous trained weights and simply train the neural network from that amount of time. So it's an interesting model. It provided one of the best results in terms of accuracy, but also it's the fastest method in terms of computational effort. So it's another interesting model, and we signal these as the two interesting models for the company, iForest and the autoencoder reuse. Just to show you the graphical evolution through the 20 iterations. So these are the AUC values. One means a perfect classifier. We can see that isolation forest is almost close to the perfect classification, and the autoencoder reuse is also, although it slightly diminishes after the 9th iteration and so on. In this example, we show a particular rock curve for iteration 3, and it shows the discrimination capability of two selected classifiers, the autoencoder and iForest. The results are very similar. What happens here is that in this particular case, the autoencoder is slightly more sensitive, and the isolation forest is slightly more specific. But both are much better than the random classifier, which is provided by this baseline model. As for the secondary goal, we selected for the same iteration one example that we knew was a failure, and we set a threshold as the average training deviation error plus 1 standard deviation. So the value is different for the iForest and for the autoencoder. But once we define the threshold, the method can automatically signal where within the curve there was an anomaly. And what is interesting is that in both images, although there are two different learning methods, both tend to select the same regions, which are typically regions of failure. So there's here a kind of a huge valley that suddenly appears, and this is a clear indication of a screw failure. And at the end of process, there's also an abrupt decay in the torque value, also signaling a huge decay. So to conclude,
he left.
Okay, I'm finishing. To conclude, iForest provides the best supervised anomaly detection results. The autoencoder reuse is slightly worse, but it's much faster computationally, which is interesting if we try to apply this in a real-time environment. In the future work, we wish to explore more autoencoder architectures and also try to use something that is costly, human feedback, to actually label the faulty cases and label the regions where the faulty cases are, so we can better analyze the secondary goal. And thank you all.
Thank you, Paolo. Thank you for this presentation. Just see if there are questions from the people, also in chat. No, I just have one from my side to you. What do you mean with the Adm method require much less computational effort? Can you quantify that in respect to the method that you showed during the presentation, or which are the most common one?
Yeah, it's on this slide. So the training time for the 2 days of data for isolation forest is 168 seconds. The autoencode is just 23 seconds. So if you do a simple computation, it's worth what it's worth, but it means that basically the autoencoder is 7 times faster in terms of training. And if you have a huge amount of data, instead of working with 2 days, if you work with 1 month of data, which is really big, then it probably will make a difference computationally.
Many thanks for the explanation.
Okay.
Thank you.
Okay.
So, waiting for eventually question. 3, 2, 1. Thank you, Paolo. Thank you for your contribution, for your time, and thank you again. So, the next speaker is Cecilia. Cecilia, are you there?
Yes.
Perfect. You can start sharing your screen. And then we will start with your presentation. And Cecilia, we will introduce to us the contribution named Object Detection with RetinaNet on Aerial Imagery. So, yes, we can see, but not your presentation, Cecilia?
No.
No. We can see all the list of the people in Jitsi. Try again.
No.
Now, yes.
Okay.
Perfect. Cecilia, the floor is yours. 15 minutes in total, and I will tell you at 2 minutes before the end.
Okay, thank you. Good afternoon. My name is Cecilia. I'm going to present you the work entitled Object Detection with RetinaNet on Aerial Imagery, the Algarve Landscape, which is a joint collaboration with Fernanda Costa, Luís Ferraz, and Ana Jacinta Soares, all from the Center of Mathematics of University of Minho. The motivation of this work is the detection of swimming pools in satellite images to fight tax avoidance. This is done by developing an autonomous solution able to deliver high performance in real case scenarios. To do this, we studied several deep learning algorithms to do object detection, in which we chose the RetinaNet for its characteristics. So we decided to train different RetinaNet models with different backbone architectures, with different depths, in order to check which one would be the best at detecting swimming pools. We constructed a training data set and trained the models, and then to evaluate the performance of the models, we built different testing sets, and we test the models with those testing sets. So the first data set we created was the training data set. First, we...
Cecília, estamos a ver o primeiro slide ainda.
Okay, we are still seeing the first slide, at least the title. It is okay or not? I suppose.
No. So you are seeing the...
It seems that it is freezing. Okay, go on. I see the mouse going on.
Okay. I changed. No. Maybe I'll stop.
Okay, name, motivation, and goal. We are.
Okay. And it's okay. And now I skip again. It's training data set now.
No.
Not yet.
What? How about now?
Now, yes.
But this is not full screen, right?
It's not in full screen. No, it's not in full screen.
Okay, but can I do it like this? Because this is working and the full screen is not?
No.
I don't know why, but it seems not working at least. But
the full screen, yeah.
But you can continue in that way because it's at least I can read.
Okay, then I'll continue. So first, we developed a training data set. We took a training set from the platform Kaggle. It had 3,748 training images, and each image had a Pascal-Voc annotations file. Those annotations had annotations for cars and swimming pools. Since we only wanted to detect swimming pools, we had to pre-process the data set. So we developed 3 Python scripts to do that. One, to delete the images that only contained cars and their correspondent annotation files. A second one, to remove the annotations of cars from images with swimming pools. And a last one, to convert all the annotations files into a unique CSV file. After applying these pre-processing steps, we got a new training dataset composed of 1,993 images. This training dataset was then used to train 3 different RetinaNet models with different backbone architectures, namely ResNet 50, ResNet 101, and ResNet 152. Being ResNet 50 the shallowest and ResNet 152 the deepest. In the end, we got 3 different RetinaNet models capable of doing the detection of swimming pools. To test these models, we developed 3 different data sets with different characteristics. We gave these data sets to the 3 models, and those models gave their predictions. In order to compare those performances, we built a confusion matrix that has 4 entries, a true positive represented by TP, when a model detects an object as being a swimming pool, and it actually is. True negative, when a model doesn't detect an object as being a swimming pool, and it actually is not. False positive, when a model detects an object wrongly as being a swimming pool, and false negative, when a model wrongly classifies a swimming pool as not being one. With the entries of the confusion matrix, we were able to compute 6 performance metrics: accuracy, precision, sensitivity, specificity, and type 1 and type 2 errors. So the first testing set was based on the training data set we took from Kaggle. So the images are very similar to the ones used to train our models. It has 2,703 testing images, and the images had no annotations. Since we wanted to evaluate the predictions of the models, we needed to annotate the data sets by hand. So to ease that task, we developed a Python script to annotate the testing data set by reading mouse clicks as bounding box coordinates, and to extract important information from the images. In the end, we know that the images contain 620 swimming pools. This testing data set was given to the 3 models. We have the results of the confusion matrix entries and the performance metrics in table 1. As we can see, no model stands out. They get very close performances. So from this testing data set, we cannot be sure which one is the best, being all perfectly well at recognizing swimming pools in satellite images. So we decided to develop a second testing set, this time a testing set that would mimic a real case scenario. So we cropped images from Google Maps from the Algarve region in Portugal, because this region has a very high density of pools. We have 289 images with different sizes, zoom percentages, and quality. And in total, it has 298 swimming pools. To collect the data, we developed one Python script to split one big image into smaller ones with random sizes. And again, we used the Python script I talked earlier to annotate the images. Notice that these images were not carefully picked. As we can see, there are images that have swimming pools half hidden. There are objects that look like swimming pools, and even empty swimming pools. So this testing set was given to the three models, and we have the results in table 2. We can clearly see that the RetinaNet model with the ResNet 152 is the best. It has very high performance values, and ResNet 101 and ResNet 50 have very low performance metrics. As we can see, ResNet 152 by far recognizes 100 more images, swimming pools, than the ResNet 50 and ResNet 101. And notice that there were in total 298 swimming pools. So ResNet 152 got really close to that value. So we can conclude that the model with a ResNet 152 is ready for real-life case scenarios, while the other two are not. To finish, we decided to develop another testing dataset, this time to do a more qualitative evaluation of the models to see in which situations the models have difficulties. So we carefully chose some pictures from Google Maps. We chose 8 images with different sizes, zoom, and quality. We can see the images are these ones over here. We can see that there are unusual colored swimming pools like green. There are very small images, objects that look like swimming pools, but they are not, and a lake. So this testing dataset was given to the models, and the predictions of the models can be seen by the blue bounding boxes that were drawn by each of the models. From these predictions, we can see that the model with a ResNet 52 and the model with a ResNet 101 have difficulties in recognizing green swimming pools. And the model with a ResNet 52 is fooled by the blue basketball court. Also, the RetinaNet with the ResNet 52 and the ResNet 101 have difficulties when the images are poor quality, even when the swimming pools are perfectly normal, blue and rectangular shaped. The model with the ResNet 152 only has difficulties in very small images. To conclude, the goal was to develop a deep learning model for the detection of swimming pools in satellite images. To do that, 3 RetinaNet models with different backbone architectures were trained, namely ResNet 50, ResNet 101, and ResNet 152, being ResNet 152 the deepest and ResNet 50 the shallowest. One training dataset was used after preprocessing an existing one. To evaluate the model's performance, 3 testing datasets were created, one more difficult than the other. And to conclude, the results showed that the RetinaNet model with the ResNet 152 is the best at detecting swimming pools in satellite images and is ready for real-life usage. Just a final remark, if you want to check the data sets created for this work, they are publicly available. At Kaggle, you can look for swimming pool detection satellite images for the training and first testing dataset, and the second testing dataset is called Swimming Pool Detection Algarve Landscape. Thank you.
Thank you, Cecilia. Thank you for the nice work and also for the nice presentation. Waiting for a question, if there are, from the online people, also in the chat.
I can ask.
Please.
Okay. Cecilia, in terms of the evaluation metrics, why didn't you use the ROC curve? Because the confusion matrix assumes a fixed labeling, but I assume that deep learning models can be used to assign probabilities. And if you have probabilities, you can have a more flexible definition of sensitivity or specificity. So that's one question. The second one is, the data sets sound interesting, and you have crafted some to show where the models can fail. But what would be a data set that you feel that would be enough to validate the models? Because the number of different pools that you tested seems to me somehow low.
Okay, thank you for the questions. Maybe I'm going to start by this last one. The testing data set that I'm most confident about is the second testing data set, the one with images cropped from Google Maps, because it definitely is a real test case scenario. That's what people in real life are going to do. They are going to open Google Maps and just extract some random images and give to the model. It's true that the number of swimming pools is low, but actually the number of swimming pools is not. There is not a region where I can randomly extract images where there is pools in high density. So I needed to handpick each image to
yeah, but one interesting approach would be using gamification, where you could devise a game and put students or colleagues classifying images. That would be a fun way. That's just a suggestion.
Yes, that will be great, because annotating the images is not funny at all. I don't know if we have time.
Sorry, guys, but we have 5 minutes delay.
Okay.
I have to stop, Cecilia. Sorry for that, and I have to leave the place to the next presenter in the room. Sorry to stop you again, and
okay.
what a really interesting work. Thank you for this, and so I can leave the floor to the next presenter, which is from here, from the agenda, Elisabetta. From here, are you there? Elisabetta?
Yes, I'm here.
Hi, Elisabetta. Hi. So please share your screen with your presentation, and in the meantime, I will present you. Elisabetta will speak about, we will present the work in identify anomaly detection pattern from log file, a dynamic approach. Okay, Elisabetta, we can see your presentation. It seems that is not full screen, or yes?
Yes. Can you see the full screen? Maybe I have to.
Not proper for full screen. Just try again.
I have on.
Just reduce the percentage, or because here is not full screen, or you put full screen, or you have to reduce the percentage of the zoom.
Oh, okay.
Okay.
This is fine.
Yes, this is fine from my side at least. Please, the floor is yours. 15 minutes, and then I will come to you with 2 minutes from the end.
Okay, thank you. So this afternoon, I'm going to talk about this topic. So the work done to identify anomaly detection patterns from log files. So during this presentation, I'm going to describe the background and the objectives of the work. I will describe the methodology we adopted to perform this study, showing the results for a very subset of cases, and finally I will conclude. The place where I work, Janefek NAF, in the recent years started a local challenging project in order to on log analysis for anomaly detection, in order to determine and achieve an early and faster diagnosis of potential problems. And this project uses various services that run at the data center on the available machine. There are more than 200 services, and the machines are used by experiments, different experiments, some of them belonging to the community of the Large Hadron Collider at CERN. The data sets have different forms, log files, but also CSV for specific metrics that came from different sources like InfluxDB and RCS log, the second one for the log files. And the activities are various. Some of them have been included in the IO Twins project, and Alessandro Costantini is going to talk about this project in the next presentation. Some other are specific for services like STORM, that is data management service used by the LHC experiments to transfer and access file, and LSF batch system, that is the service used to work with jobs. There is another activities that intends to design and implement a big data platform where it is possible in the end to perform this kind of analysis both on offline and online data. The work performed in this study is based on log files and the problems that are stored in these files. So far, we have considered more than 3 million of logs in a long period of time. So a log file contains insights on the service activity, service that runs in an operating system on a given machine. In our case, the operating system is Linux-based, and the file reports the internal state of the service. Furthermore, the log files keep trace of the events that take place on the system in order to, and this information are useful for monitoring, troubleshooting or debugging, reporting, and mining. By analyzing this information, it's possible to determine if a service is up and running or if it is eating memory. If the service is quite slow, or if a user is authorized to perform specific operation. The log file usually contain a set of information such as date or timestamp, source of name and IP address, service name or process ID, log level verbosity, like info, debug, warning, error, and the message itself. The message is a natural, can be considered as a natural language text that contain information according to the specific service, and the form of this log sometimes depends on the site administrator's policy. It is not easy to understand the content of this message. Unfortunately, there isn't an official standard that can be used or adopted to produce this kind of log. So this is another problem when we need to parse the information content in these messages. And usually the messages is composed of a dynamic field and a static field. The dynamic field is a string or a set of strings that are assigned at runtime, while the static field does not change during events. The field in the second case can be delimited by, in both cases, can be delimited by different separators, like the white space, as in this case, the figure that is shown in the right side of the slide. Okay, here is reported a screenshot of the crondy log file that the service that runs on a specific machine at the data center. The specific machine is recognizable by the host name. In this case, it's used a specific acronym that is WN, that stands for worker node. So it is easy to recognize the type of machine where the service is run. And this type of information, the category of the machine, can be useful in order to identify the similar problems or problems on a specific machine. This type of files is then transformed in a CSV form before performing the analysis. Another type of information that can be collected by analyzing this type of file is the long event type and the anomalous key terms. The idea is to collect for the various event types, the various key terms that are useful in order to determine bad behavior of a service. So here, for example, is the log event is error, and the key term, the anomalous key term, is reset. Another log event is fail, with the key terms that in this case are true, connection, and timeout. For other type of services, it's possible to identify other key terms like abort, alert, and stop, and so on. We are collecting all these type of key terms for all the logs files that we have available at the data center. So in this study, during this study, we aim at defining and building a model able to identify anomaly detection in a certain period of time on log files once transformed in CSV form. And we combine different machine learning techniques according to the steps we are going to perform. We use natural language processing in order to detect the feature space and feature matrix and anomalies. We apply the autoencoder technique in order to determine if we were able to reconstruct the original messages, and the invariant mining technique in order to combine more than one feature from the CSV file with the messages. In our study, we used, for example, the host name and the messages in order to determine the anomalies in a specific period of time. The approach that we follow is summarizing this figure. Basically, once collected the log files from the machine, we create the features performing data preprocessing and feature transformation. At this point, we were able to use a matrix, a feature matrix, as input to the machine learning techniques. To validate the models, we use new log files, new entries for the specific service. And finally, we detect anomalous entries for specific service. So here I summarize the first 20 log files per frequency available at the time of this study. We decide to exclude log files of services with a frequency lower than 1 month, because we consider not important for the study. And we started categorize the log files per type of machines in order to be able to perform complex study soon after finish this one.
Elisabetta, 2 minutes left.
Here is reported the the file transformed in CSV form. At this point, we remove from the messages text that are not considered important. Here is reported the example of the feature that we obtain applying the NLP methods. As you can see, each text is transformed in a set of terms, and one value is where the terms appear in the messages. Here I summarize the results of the machine learning techniques. As you can see, the results are similar. We get good result with the NLP word-to-back techniques, but also the other two techniques are considering promising in order to determine the anomalies. The data here are for 2 consecutive months of data in the period June-July 2020. And the results are for a subset of services, including the cron-D file service that I saw before. Here I summarize the set of anomalous messages that we identify, for example, in the cron-D service. Here are reported the set of anomalous terms that appear in a specific period of time by applying the invariant mining. And in conclusion, we consider promising the result we get by applying just these three techniques. F measure is over 86%. The model that we build is able to recognize problems in the analyzed files. With the result that we get, we think that is the right moment to receive feedback by the set administrator in order to be able to understand, to have a better understanding of the anomalies that we have identified. We have started extending the study to all the services available in the data center with a frequency greater than 1 month. We intend to combine the matrix that we get from the log files with the matrix that came from other sources like InfluxDB in order to determine if it is possible to, for example, identify when the temperature of the data center increase according to some anomalies that appears in the machines. We also intend to use to apply online approach in addition to the offline technique.
So Elisabetta, the time is over. I have to stop you.
Yeah, I'm finished.
Sorry about that, but we are also, the time is over. We are also in late of 10 minutes. Thanks for your presentation. There is unfortunately no time for questions, but if you like, I can give you the chance to say write the question in the chat, and maybe Elisabetta can write back the answer. Thank you, Elisabetta, and sorry for this. So let's go directly to the next speaker, which am I, basically. This one, share. So, okay, here we are. I think that you can see the slide. Yes, you can. Basically, so thank you. I try to be more quick than usual to save some time and to leave the floor also to the last speaker. Here I'm going to present you what we carried out within the IOTwins project, which is a cloud edge orchestration platform for innovative industrial scenarios for the project itself. Just I'm putting the time also from myself. And so here I'm speaking on behalf of a collaboration of people within the project. And as you probably know, there are some technologies which are cloud and edge and Internet of Things that are growing of interest also inside the European community. And also there are projects that use such technologies for their activities in different fields, for example, in scientific and industrial fields. Among those, the IOTwins project, which is the link is on the slide, is aimed to integrate such technologies with, and we will see how in the next slide, to define a sort of digital twins for specific manufacturing and to provide for them a sort of, let's say, platform to study the model, to integrate the simulation and data-driven model to feed the artificial intelligence services. Here, the partners of the project are 21 partners. Here, there are just the coordinators, some partners. And as you can see, there are, let's say, industrial partner as well as public partner. And Bofioli is the industrial one that is leading the project. IOTwins leverage on different aspects. First of all, the experience and the outcome of the past, let's say, cloud-based project that developed some, say, cloud-based technologies. Here you can see some of this project. On the expertise of the 21 partners coming from academic and research and private. And last but not least, 12 dedicated large-scale testbed, ranging from let's say, the twins model for the aeolic rotors to the cooling effect in a data center, and also to evacuation plan of a stadium, because Barcelona is also one of the partners of this project, for example. Here, what you can see here is the architecture of the IOTwins. In particular, you can see the different layer, the IoT layer, the edge, the cloud layer, and the authentication services. Those, the service in blue are what is called the IOTwins orchestration platform that put together, integrate together those authentication, edge, and cloud layer and the related technology. Here, just a summary of the component that I showed to you right now, and we are going to see in detail what they are. So, first of all, the authentication part. As you probably know, the authentication part is the most interesting part because it tries to, let's say, cover different technology. And we use what is called the Indigo IAM. IAM stands for Identity Access Management Services, which has been developed within the Indigo Data Cloud project, as you can show in the first slide. And then it's sustained by INFN and by the project that decide to adopt those this service. And in particular, the WLCG community at CERN that elect IAM as the next generation authorization service. Here you can see in the link, the GitHub link for the Indigo IAM service. Indigo IAM solution supports different authentication mechanism: local username, SAML, X509, OpenID Connect, and it make quite easy integration with many services, thanks to this different kind of support for authentication. OpenStack, Moodle instead of Kubernetes, Grafana, and so on and so forth. On the right, you can see the credential for the IAM, and the dashboard can be customized with the logo of your institution. IAM is also comes with a dashboard for an easy and intuitive operational activities, and the important part is that support group management, group and subgroup management, and is able to give different rights to different people. And also, as the other services that we'll see in a while, it is exposed by REST APIs. The orchestration layer, the cloud orchestration layer. So we have this pass orchestrator, which is also a development that has been developed during the project that you can see in red, and is aimed at provision the virtualized compute and storage resources with different framework coming from the cloud and framework coming from abroad, and is on the service level agreement criteria based on the user. So what the user can do or cannot do within the service level agreement defined with the framework itself. Here you can see the high-level architecture of this pass orchestrator, which is exposed by REST API as all the services that we show you here. And the most important part is the orchestrator, as you can see in the middle of the figure, and the so-called adapter and connector that are a sort of plugins that are able to, let's say, integrate and dialogate basically with different kind of resource and technologies. Let's go to the edge layer. As you probably know, the edge layer are those software that provide services that able to communicate with both the Internet of Things and the cloud level. And to do that, we adopted in the project the Apache Mesos. Apache Mesos, as you probably know, is an open source project to manage computer cluster, which has two frameworks basically. Marathon, which it takes care basically of the container orchestration, and Chronos, which is the fault-tolerant scheduler for the job orchestration. Here you can see the cloud edge orchestration integration activities and high-level stuff, where that is provided by the pass orchestrator components, and thanks to that it is possible from the pass orchestrator to deploy and make available services on both cloud and edge layer. So you have just one, let's say, controller in order to do that. As I told you before in the previous slide, IOTwins is a use case driven project, and we provide for the users a dashboard and pass orchestrator dashboard, and the user has been able to define their proper use case and to use the use case itself. And at this moment, the user can say can use two different kind of deployment services. The first one is the deployment of a service on top of a cloud virtual machine and use OpenStack, for example, framework or other kind of cloud framework, and deployment of services on top of the edge node, thanks to the integration with Mesos and its frameworks. Moreover, the user can also control the status of their job on their deployment and see for details, for the logs, and control why and where it is, for example, failed. Just let me conclude with the last slide. In this presentation, I presented you the outcome from or part of the outcome in this way of the IOTwins project. As I told you, this IOTwins project is a project aimed to, let's say, define and study and apply hybrid digital twin model and provide for them a suitable platform to let the user study their own digital hybrid twin models. And